Good afternoon, Ashok.
Good afternoon, Shankar. Good afternoon.
Hi.
Welcome everybody in this presentation of Dr. Upendra Singh. So just another 2 minutes shall we wait? I think it's 3:57. 3 more minutes we'll wait, and exact 4 o'clock we'll start. So please be with us. Dr. Upendra Singh, you are here, no?
Sir, I am very much here.
Very good.
I am busy
Very
with some
good.
other work.
Very good, very good. Because your question answer session will require you. Kurt is also here. Are you coming to India or good morning? Are you coming to India or not? Main question. Okay, we'll discuss later on, maybe. Okay, George is also here. Hello, George.
Hi, George.
George will be in India in Bhubaneswar conference. So we'll look forward to meet him. Hello, ladies and gentlemen. Good morning, good afternoon, good evening. Today we have Dr. Upendra Singh with us, who is going to talk on the topic of extraction of strategic critical metals from aluminium industry waste. I will not giving him full introduction, but he is the head of the analytical department. And as I know, he is the person behind setting up many things in JNRDDC, which made it a profitable organization. And today, JNRDDC people are getting salary thanks to Upendra Singh, because he is a very enthusiastic, very much motivated person. And today we have roped him to talk about this critical metals from aluminium, waste of aluminium industry. So this may be about 50 minutes presentation, and this will be followed by questions and answers. So I will request Priyanka of IBAAS office to start the presentation, which is a recorded presentation, and then it will be open for the discussion. Thank you very much.
Respected convener of this lecture series, and a special thank to IBAAS and Nandi Saab for giving me this opportunity to speak on extraction of strategic critical minerals, metals from aluminum industry waste. So I am Dr. Upendra Singh. I am a senior principal scientist at JNRDC, and I'm also heading one of the department, that is analytical of the center. Now I'm going to speak on extraction of strategic critical metals. Why it is important at the at moment, because Ministry of Mines and even Government of India is especially very much keen to see the opportunity in any secondary resource where we can extract critical metals. So what is we thought of that, why not we think of aluminium industry wastes, aluminium industry byproducts. So regarding extraction of strategic critical minerals, we have chosen this topic, and I will go one by one. First, I would like to give a brief introduction about the critical minerals. Specifically, these are metals only. But why it is important with respect to aluminium industry, that aluminium industry itself generate lot of waste, and even in the circuit, bare process circuit, you can see even thousands of meter cube liquor is circulating. So if any plant which is older, I think if you can go with the start of the plant and then current status, there are several critical metals and trace elements are rotating, or you can say circulating in the circuit. So our objective of this presentation is to give an overview of those critical metals which are there in the aluminum industry, specifically in red mud and bare liquor. So we have selected three. One is vanadium, another is gallium, and third one is the scandium. So why it is important? Because these metals are very much found in the this aluminum industry, liquor and red mud. So first I just give a brief introduction about the critical minerals. These minerals are very essential for our country for so many reasons, but most important reason is strategic, economic and national security. Why? Because these metals are very much required for our domestic requirement, and because of their limited availability, the and supply chain vulnerability, it is very difficult to get from the other countries. So global significance, I would say, critical minerals like lithium, graphite, cobalt, titanium, rare earth elements underpin future global economics. This is very true. And why not we think of these three, that our vanadium, gallium, and scandium. So you see, Ministry of Mines, Government of India has identified 30 critical minerals, whereas 24 has been identified for the auctions. So at the current scenario of India requirement, this is very much important to see the opportunity from the secondary uh, industries, specifically aluminium, primary and secondary industry is specifically aluminium industry, where we can see the opportunity in the West. So Indian bauxite, I am going into the background of the this presentation. Indian bauxite also rich of trace elements, and very much you can see chromium, vanadium, gallium, zirconium, even lead also sometimes, rare earth elements, etc. Rare element I am talking about, if you go with the analysis or characterization of red mud, you can find that around 50 to 70 ppm, specifically Central Indian bauxite processing red mud, is having 70, around 70. If you see, specifically I can say Muri, Hindalco, Muri plant is having around 70, whereas in Renukot plant, red mud is having around 50, 55. But in case of East Coast processed bauxite residue, or bauxite residue means red mud, is having around 30 to 35 milligram per kg. So these are the challenges, how to recover those. And in bare circuit, you can see gallium and vanadium both are in good quantity. Specifically, Hindalco based or Aditya Birla Group based plant is having more of gallium than Nalco and Vedanta. As per my knowledge, I think Hindalco is having more than 150 milligram per kg, whereas in case of Nalco and Vedanta, it is not more than 110 or 115, something like that. So this is a very good opportunity nowadays, that how to extract it. The distribution of trace elements in Indian bauxite deposit is there. You can see in this slide that vanadium is found to be around, this is in bauxite. So red mud, it is normally in this, equilibrium solubility is there, and if you are going with the digestion, the solubility of some of the elements which are very high and some are very less or even very negligible, like titanium doesn't go into the liquor. But vanadium, gallium, potassium, all these metal elements are going into the solution, which normally rotates throughout the year, so many years, and it is built up. Normally it build up in the circuit. So at one time you can find that it is a critical concentration where you can extract. So any concentration, like if you talk about gallium, if it is more than 140 or 130 plus, I think it is very viable kind of thing where we can extract. There are methods and people are working upon it. So you see, vanadium is like 100 to 1500 ppm. Chromium is also very good concentration, manganese, nickel, cobalt, zinc, copper, and gallium also you can see it is 25 to 110 ppm. In some cases it is found, but usually if you see the normal value or optimal value, it is around 50 to 60 milligram per kg or ppm. So zirconium also you can find. Cadmium is less, molybdenum, bismuth. This is a typical result or information where we have collected from our own resources. And scandium and Re, it is there that 0.01 to 300 ppm. So this is a typical information which I want to share with you. And in RE specifically, scandium is very much required. And since I just told you that is it around 50 to 70 ppm, even in, because there is no primary source of scandium as such, so it is a very good source for recovery of scandium from the red mud. In bauxite, usually it is coming around 15 to 25 milligram per kg, but because of the processing, it goes and it doubled, mostly doubled into the red mud, and it is found to be around 50 to 70 milligram per kg. So it is high time to think about the extraction processes for these three metal elements present in aluminum industry, bare circuit and red mud. So during digestion time, you can see, just I told you, the trace elements go into the solution, but because of the solubility and it's the equilibrium solubility, most of the elements goes into the solution, and some of the elements, or maybe 50% of the trace elements, going into the red mud. So these elements, as I said, enrich over a period of time. If it is a plant is 50 years old, accordingly the buildup is there. So vanadium and gallium can be economically be extracted from the spent liquor, and spent liquor volume, if you see, it is going to be very high. If it is more than, I think, 5,000 to 10,000 meter cube in one plant, and if you calculate based on the volume, even if it is 100 milligram per kg, it is in maybe in tonnage. So that is what the things which one have to think of. So gallium I am talking about first. It is a strategic metal, and most of the use is defense application. So optoelectronics and defense. So there is no primary source of gallium, as I said. So this is one of the area where bauxite and bauxite residue bauxite processed liquor can be the source of the recovery of gallium. And as per my knowledge, uh, Hindalco has already, Renukut plant has already started long back, and they stopped in 2004, I think, because of some reason, because of the process impurity, and because purity is also, that gallium purity was not achieved to be 99.99, and mercury poisoning was also there. So because of that reason, it was stopped at that time. But again they have started. I think Muri plant is going to set up the gallium recovery using some ion exchange. So this is how it is going on. But Nalco is also thinking with the bark technology. So these are the things which are under progress, and hopefully in coming days or coming years, we have a good recovery process in India, particularly from the bare liquor, specifically gallium. But vanadium is already there. Hindalco is recovering vanadium as a vanadium slush. There is also some issues because of soda content and all, but that is also a very good recovery. So it was discovered, I am not going into the detail. It is also discovered in the France, and gallium was discovered spectroscopically, obtained as a free metal by electrolysis of the solution of actually gallium hydroxide. But you can see in bare liquor also it is found in sodium gallate. So this is how I think we can think of the recovery and extraction processes for gallium from the liquor. Earlier it was extracted from the solution of hydroxide of gallium. So the gallium is only metal except mercury and cesium and rubidium. These are three other metals which are normally exist at means they are exist as a liquid in the room temperature, at the room temperature. So that is why make it possible to use the high temperature thermometer using these material. And gallium uses, these are the semiconductor material. So that is why it is very important, and there is no any primary source. So I think aluminum industry is fortunate enough to have this kind of metals in their processes, bare liquor and red mud. So extraction process I am going to talk about. The extraction of gallium from the bare liquor can be made by the following methods. This is basically a standard methods which are normally conventionally people have been using and used in the past. But there are some limitation of the these processes also. At the same time, they are very useful for the recovery and extraction also. So carbonation and electrolysis was the first one, and electro deposition, this is an electrochemical method, and amalgamation. This is what the people were using in Hindalco, Renukut in the 80s or something in that period. And liquid extraction is a new, and another you can say this is a solvent extraction, but another is now people are using a ion exchange resin. This is very, now it is going to be very good that people are now thinking of ion exchange resin, and which is very suitable. And one of the one of the institute in Ukraine, that is JSC, they have already developed a process for extraction or recovery of gallium using ion exchange resin. So this is what the new things which people are going to take the advantage of the processes which is developed abroad and even in India also. So the recovery of gallium from bare processes, usually it is very written relatively high content of gallium between 200 to 600 mgpl, but I am telling you even 140 plus will also be very useful for the recovery, and past processes will be viable. This is normally as per the literature and experience from the abroad recovery processes which are already available in the market. Can be made direct electrolysis of this solution by solvent extraction and ion exchange. That is what I am trying. In this case, what are the process steps we have to see? That it should be treated first, just to make it more concentrated. Then amalgamation is there, then leaching is there, and then electrodeposition is there. So these are the processes which I have already talked about. This is a flow diagram. Is just a basic flow diagram that how process is taking place, and it is something like electro deposition and amalgamation process. This is most common method in the many industries long back, but now it is not being used because of the mercury is one of the more hazardous and poisonous toxic elements, and if you can avoid, it should be avoided. So this is how the plant works, like a plant bare liquor, then gallium concentration one has to think, then agitated mercury electrolytic cells is required, make up mercury is there, then gallium and mercury amalgamation one has to take place, and how to make up the sodium hydroxide concentration for solubilization, because normally gallium is soluble in sodium hydroxide because of formation of the sodium gallate. So this is how the process is taking place, and in the solution filtration and finally electrolysis is taking place, where crude gallium metal is found to be obtained, and normally obtained, and it is maybe around 99 point not 9, but it is coming to close to that purity. The reaction which involved in this, that gallium from the bauxite is dissolved during the leaching phase with sodium hydroxide, and this is the equation, which is chemical equation normally takes place, where sodium gallate is being formed, and again further sodium carbonate and then gallium oxide react with water to form hydroxide of sodium gallium. The typical distribution of gallium in bare process, if you see, it is a very old data. Now it can be updated, but since I am trying to tell you that how it goes into the solution with different unit operation. So if you have aluminate solution having dilution, after dilution, before dilution it is coming to be suppose 80. Actually 10 years back or 10 or 12 years back, when we used to analyze NALCO beer liquor, that is spent liquor, we found that it is coming to be 70 to 80 milligram per liter. Whereas aluminate solution after dilution coming to be this, and then after filtration and washing it comes to be 4 milligram per liter. This is a typical information which we collected from the industry side. And washing of aluminum hydrate is coming hydrate coming to be 12 milligram per liter. This is How? And ammonium hydroxide, it is coming to be 8 milligram. In alumina, normally, typically, it is found to be 10 milligram per kg. Usually, it should be written in 10 milligram per kg because it's solid. And in red mud, it is 20 milligram per kg. So this is how it is normally distribution takes place. So how chemical separation takes place, where filtrate result in separating aluminum hydroxide precipitate is treated with it's a hydrate which is normally treated with alkaline ferrocyanide, and precipitation of gallium and gallium ferrocyanide takes place, which is this equation you can see. Gallium usually found in 3 states and then ferrocyanide in 4 states. So it comes to be a complex coordination compound of gallium, that is gallium ferrocyanide, and through strong calcination it can be again decomposed and it will come as a gallium oxide and iron will be separated. So this is how normally chemical separation takes place from the gallium. This is a polarization curve normally when people work for the electrochemical deposition or electrolysis. We need to have a cyclic voltammetry. In cyclic voltammetry, what will happen? There is a minus and plus polarization where voltage from minus some millivolts or millivolts to volts, or plus to get a the deposition potential, where normally it is demonstrated in this particular slides. So cathodic curve and cathodic curve for platinum electrode is being used here, and 1 molar NaOH is being used, and gallium is 0.6% gallium and 0.9% gallium scanning rate. Scan rate is just to see whether there is any linearity of the current, anodic current or cathodic current is there, because normally it is a diffusion control process, and in diffusion control process normally Likovich equation is being used, where if you plot a curve between scan rate and anodic current, it should be a straight line. So that is what this particular slide is being shown to for your information. There is no large scale gallium production in India. Gallium is recovered as a byproduct, as I said in my previous earlier talk, that while producing alumina, this is normally a byproduct which can be recovered. And Hindalco, if you see, a capacity of gallium refinery plant was set up in long back, and at that time the 0.012% means more than 120 milligram per kg was gallium at that time, 20-25 years back. Nalco gallium is very less, but this is a old again old data. And if I remember in the current years, like 2-3 years, 4 years back, it was coming to be 115 milligram per kg. So now it is increased to within 10 to 15 years, it goes around 15 to 20 milligram per kg increase, from around 90 to 116. So bauxite, this is again a information which I wanted to share, that what are the resources from bauxite and how much gallium quantity is there which can be recovered. So Australia, if you see the resources, China, even India also, it is 2,300 million tons of resources are there, where we can recover this much of gallium based on the concentration of gallium. So this is how this information is useful for you to know, and you can note it. The world demand has been strongest in optoelectronics application, particularly in light emitting displays. Now LEDs are very much important in the current scenario in the world, because people are going into the LEDs. And again, defense is one of the area where semiconductor chips, small chips are required. So these are this element is very important, and metal is very important. The cellular telephone market was responsible for principally, when cellular market was there in that case only growth of gallium was regarded, and people have seen The current production capacity of alumina in industry recovering have capacity to recover 3 to 4 tons of crude gallium. It is feasible, which can give at least 2 to 5 times of electronic grade gallium from the Indian industry itself. So now I'll talk about vanadium. Vanadium is a scarce element. This is very true because normally these are also very limited resources. So it occurs in association with titaniferous magnetite ore. Normally it found in titaniferous magnetite ore. Vanadium is also concentrated in many end product of organic, including coal and oil, but very limited. In addition, vanadium can also be recovered as vanadium sludge from liquor. This is what I wanted to tell from this particular presentation. Now, I just tell you that this is a very, original or preliminary information, primary information for vanadium, that how it is discovered, where it is discovered. As gallium was discovered in France, it is discovered in Sweden. This name normally used to Scandinavian mythology, that is Venus, that is a goddess of beauty. And I don't want to tell where it is found in the periodic table. This is a atomic number 23, period 4, and group 5 of the periodic table. Bauxite in India is having 0.05 to 0.2%. In titaniferous magnetite, it is very high because it is a ore of titaniferous, but it associated with vanadium, so it is coming to be 1.6%. In crude petroleum, it is 350 ppm. In phosphate, it is coming to be 0.35 to 0.54 ppm. This information is we have taken from the literature itself. So vanadium bearing titaniferous magnetite ore are the main area where we can have in good quantity. India has approximately 14 million tons of this ore containing 0.2 to 0.4% vanadium. 66% of the ore in Simoga, Hassan district of Karnataka, it is found. 15% of ore in Bhandara district of Maharashtra, very near to our place. And 19% of the ore in Mayurbhanj district of Orissa. So this is how distribution of this titaniferous ore is there in India, and source of vanadium we can see. The waste product of aluminium industry, red mud, is having 0.1 to 0.3% vanadium as a V2O5. Vanadium contained in bauxite varies from 0.0 to 0.6, but it is normally 0.04 to 0.3%. But this is a maybe some cases we may find more than 0.5 or something like that. So 30 to 40% of vanadium contained in bauxite dissolve. As I said that if you go into the detail of the solubility or equilibrium solubility of different trace elements, this is around 50%, but the vanadium goes into the 50% goes into sparingly, or no, it's a good solubility, not sparingly, you can say it's solubility is good. And 60 to 70% vanadium contained in bauxite remain in red mud. So this is how it is varying. So maybe 50 to 60 at the moment, but it is half and half. You can say that half is going into the liquor and half is going to the in the mud. So vanadium dissolved in form of sodium orthovanadate. This is normally people talk about sodium vanadate, but it is in ortho position, an ortho compound. So it is sodium orthovanadate. So recycling of Dyson liquor in Bayer process, and this sodium orthovanadate get enriched corresponding to equilibrium solubility, what I was talking about. So now we have started in our own place that how to characterize scandium, gallium, vanadium. So we have used a modern method of analysis, that is basically if you see long back, some 20-25 years back, there was a method, normally classical method people are using, and it was very difficult to analyze correct. Means methods are very good, but the people who are doing the analysis is the problem with them, that how to standardize the method and how to calibrate the method, or how to standardize the chemicals and methodology, if it is a spectrophotometric, or maybe after titration and colorimetry kind of thing. So that is the problem with the characterization. So we have been using very modern methods. Now we are using ICP, OES, MS and all. So now we are very much confident that whatever results and whatever value is coming, that is true to the value which is there in the liquor and solids. So this technology wise, I am not going to take the principle of this technique. This is known, and people may go into online Google and will get all the information. But we have all three machines based on the ICP, ICP-MS OES, ICP-OES, ICP-MS, and we have again second ICP OES, MS is there with us. So we are very much confident that how to check the value of gallium, vanadium, and scandium correctly to the true to the reported or true to the value which is there in the solid and liquor. This is how standardization we normally do for the chemical analysis, specifically these trace elements and critical metals. Vanadium content in Indian bauxite, if you see in bauxite of Maharashtra, what is deposit of Maharashtra, exactly I don't know the place, but Maharashtra, it is there. It is coming to be 140 to 204 ppm, milligram per kg. In Gujarat, it is 145 to 253. In Savarkanta, it is Kaira, and it is 200 to 700. So this is how you can see the variation is taking place in bauxite. And Madhya Pradesh, it is going to be 100 to 325, and Jharkhand, it is 300 to 600 ppm. But as per my experience in the past, these values are very less, and maybe it may be now, if you check the value, this is a old value, you can find that it is coming to be more than 500 ppm in all sort of bauxites which are available in India. So the vanadium sludge obtained, this is normally in Balco, when it was they have obtained the vanadium sludge from their liquor. It was their vanadium was found to be 10%. In Hindalco Renukut, actually I was there when this kind of work was going to take place, and vanadium sludge characterization work, actually we are also involved. So it is coming to be 15 to 18%, where this is a typical value which is shown is 18.2%. Muri and Belgaum also, it is actually same from 5% to 20% maximum. Nalco Daman Jodi vanadium sludge, because of low content, it is not very appropriate. So it is coming to be 8 to 9% in Nalco bare liquors. But even now also, I think vanadium sludge is not being generated, or maybe not recovering this aluminium refinery of Nalco. So dissolved vanadium from bauxite can be recovered in the form of vanadium crystal or vanadium salt. But the problem with this, that the soda content is also in this vanadium sludge is coming to be more than 20%. So removal of soda is again challenge, because if you see the costing and recovering, maybe you can remove, but costing will be there. So everything, if you see, it's a challenge even now also, that how to remove vanadium means soda from vanadium sludge completely. Due to a large demand of vanadium, the steel and other chemical industry, the vanadium sludge is important as a byproduct. Normally it is being used in vanadium is being used as a in aluminum steel industry. So the importance of this, because in our country we have been producing a lot of steel and iron. So this is again our domestic requirement, that if vanadium is there, we can also use for our own purpose. So sodium vanadate 18H2, normally it is there as a vanadium sludge. So you see equilibrium validity in bauxite and then spent liquor and strong liquor in aluminum industry. So equilibrium solubility and effect of other impurity and vanadium solubility is also very important. But normally I'm not going to talk about that, but the typical value which is there from Hindalco, Vedanta and earlier Balco and Nalco. So you just see in bauxite it is 0.2 to 0.25%. Vedanta and Balco, and now earlier Balco and now Vedanta, it is around 0.1 to 1.5, and then Nalco is very less, 0.05 to 8%. Vanadium in spent liquor in Hindalco, as I said, it is very high, 2.4 to 2.8, but it is more than 3 even now, because as per my knowledge, it is more than 3. And in Balco, it is 2, earlier Balco, now Vedanta. So 1.1 to 1.2 GPL in Nalco. That is the reason Nalco is not being able to recover vanadium sludge unless it is reaching more than 1.8. So very difficult to recover. So vanadium in strong liquor, you can see 3.5 to 4 GPL. But spent liquor normally it is being used. So 2.8 to 3 GPL gram per liter in Balco and 1.65 GPL. This is the typical value. At one point of time we have collected, and maybe there is a change. So we just think of this, that this is not a 100% accurate value. It may vary plus minus 10% in this. So though vanadium is found in to amphoteric in nature, solubility process after, as I said in the earlier slides, that the solubility of vanadium is 30 to 14. But in one of the project when I was doing, it was found to be around 50% vanadium dissolubility in bauxite using pure caustic. But since people are using in plant that is they spent the liquor which is plant liquor itself, so maybe because of the common hand effect, dissolution is affected, and there is a issue of solubility in plant liquor. So it may comes 30 to 35, 40%. So moderate solubility is due to presence of goethite lattice. This is why it is uh, not soluble or less soluble, because of presence of goethite lattice, which is a, a mineral phase which normally does not allow to get into the solution. So limiting solubility of vanadium as a B2O5 is reported to be 3.2 GPL in bare process, bare liquor. The solubility of vanadium is mainly depend on the process temperature, concentration, and presence of other impurity as salt. So that is the basically in bare liquor. It's a complex kind of liquor where many things is there in the salt, in the liquor, in form of salt, in form of elemental, in form of some compounds. So that play an important role in the solubility of vanadium as well. So reduction of phosphorus concentration in liquor is stabilized. But whenever vanadium is there, phosphorus is also there with that in bauxite. So bauxite destabilization usually taken, vanadium destabilization usually taken place by concentration of phosphorus. So phosphorus is equally important and culprit for the destabilization of vanadium recovery in that from the liquor. This is a vanadium separation flow sheet from the strong liquor, and this is normally, you can see, plant people can understand that how evaporation series 1 2 3 is there, then strong liquor is there 1 2 3, and then how it goes into the feed tank, and then thickener, underflow storage tank is strong. This is a flow sheet, is normally it's a normal process where people are recovering vanadium sludge from the liquor. So I think this this is a literature information from the one of the industry in abroad, and even India also almost closed circuit is there for the recovery of vanadium from the beer liquor. So these are different unit operations where the temperature is very important in this, that how much what temperature vanadium is getting means extracted, or you can say separated from the liquor, and a drop and the concentration of caustic and then concentration of vanadium itself will play an important role in separation of vanadium from the liquor itself. So worldwide reserve, you see vanadium in China, as you know, in every aspect of critical minerals, China is leading. So worldwide, you can see reserves are 13,000 tons of reserves are there, where China is leading with 5,000 and Russia is again. So China and Russia is leading in this particular area, vanadium recovery and vanadium reserve. Not recovery, but reserves. So South Africa 3,000, USA 45, but India has no any information. So people are thinking of recovering from bare liquor itself, and Hindalco is doing very good in this area. So future prospect, if you see, India is a big potential for gallium, vanadium, and rare earth production from the refinery. No commercial plant has been set up to produce these valuable metal, though it was there for NALCO set up for Hindalco, but not yet, in the last 20-25 years, no news. Earlier it was there for 20 or 30 kg of gallium from Hindalco Renukut, but at the moment it is not functional. Now they are again thinking of using ion exchange. Initially, NALCO started with 30 kg per year with bulk and secondary technology, and I don't know at the moment there is no any update that they are having this process. But I know that NALCO is also thinking of setting up a plant for recovery of gallium from their liquor using our indigenous technology of bark and all. So technology supplied by Secretary and Bagas, it is there. So domestic requirement of gallium is around 1000 kg of 5N purity. So that is the problem with gallium recovery or production using bare liquor, that it does not go beyond 99.9 or 995, something like that. It is not going 5N. So purity is an issue. So people are again thinking of a project. If any gallium is recovered from bare liquor, then how gallium can be purified. So another project is there. So cost of metal, as I said, 1,000 to 5,000 US dollar per kg. This is very important. Based on purity only, because if it is a 5 and 6 and only, then this cost will be there. Otherwise, it will be less. So recovery of these valuable metal from these liquor papers not only benefit the industry, but also help the nation. This is very common. Now I will talk about scandium. Scandium is why it is very burning topic in India, and specifically if I say our Ministry of Mines is thinking of recovering scandium, because this Niti Aayog and Ministry of Mines both are in the same thinking that one has to think of recovering gallium from their solid, that is residue of bauxite, that is red mud, and gallium content in scandium content in red mud is found to be very significant, because as per my knowledge, if any material which contains more than 50 milligram per kg of scandium will be treated as a primary ore. So when I was working in this particular project, and even now also we have a very good group of a consortium kind of thing, where 3 institute and 3 industries are working together to recover scandium. But the problem arises with that while recovering the scandium, we have to recover so many things others. So it's a kind of holistic approach where I think Vedanta, Nalco, and Indalco, and our three institutes like JNARDDC, NML, and IMT are working in the same area, and people knows the what are the things which we have done, and hopefully in coming days or coming future, maybe we have our own technology, indigenous technology, which can be useful for the extraction of scandium using red mud by our indigenous technology. And I don't want to go what are the role of rare earths, minerals, metals in clean energy demand. So this is one of the most important area where one can think of that how gallium how scandium can be extracted from red mud. As I said in the earlier slides, in my opening, remark that gallium and scandium in red mud of Central Indian bauxite processed is having more compared to the East Coast bauxite processed red mud. And global production and you can see the China dominance in particular area scandium, and rare earth specifically. So you can see that pink circle, you see China dominance. So it's more than 80 to 90% of the total production and total, uh, generation of rare earth from is China. So that is why China is playing hand and ball with the other countries, and now it has become becoming imperative to other countries to think of their own resources, whether it is a primary or secondary, to recover the scandium out of whatever waste is there or whatever primary sources are there. Just to think that China may hamper the supply chain of these minerals or metals in future. So why recycling and alternate sources of recycling? Because as I'm telling, the Chinese policy of restricted production. This is started in 2009 itself. Now growing demand of 2 lakh tons and long economic strategic importance of REs and is necessitated to develop indigenous technology for producing the rest. This is what I told. The status and scope of recycling of rare earth, that is the expanding use of RE bearing minerals, cost and environment problems associated with the waste and scrap disposal, availability of large amount of REs in waste product, focused R&D effort on the recycling of REs, availability of significant amount of RE in waste product such as bauxite residue, and this is what I was telling, it is coming to be 200 to 800 ppm at the moment, because in some of the bauxite it is found to be more, particularly lanthanum and cerium is coming to be 100 ppm or something like that. So if you combinedly, it is coming to be more than 500 ppm. In some cases, even it is more. So red mud is a solid waste, as I said, during the bare process and chemical leaching process of production of alumina. So it comes as a red mud, and you see in red mud contain relatively high amount of REs, as I said. So why not we think of this particular year? You see in the information, this is a general generation of red mud in 3 billion tons of stored globally. 120 million tons per contain high value of element, rare earth and gallium, scandium and others, and more than 10 million tons of red mud is generated in India itself. So you calculate based on even 50 gram per ton. If you calculate based on that, it will come to be thousands of tons of scandium is lying in our ponds. So why not we think of that? In this regards, we have done our center has started as a one project we have done for recovery of scandium from red mud for DST, and we have applied some techniques. Like first we wanted to enrich the scandium in one of the fraction of bauxite residue, and maybe that part treated, because usually acids are being used for the leaching process. So in that case, if the material or the processing material is less acid will be required. So our thinking was to separate into high and low value scandium or rare earths. So that part we did, and there was not a very good success, but there was some success, around 20-25%, 30% enrichment was there in one fraction. And that fraction is typically used for our process development for extraction of scandium. So we tried with three acids, but as per our experience, we found that S2SO4 in some molarity is being used for the selective kind of dissolution. And also the advantage that iron, which is very in high quantity in red mud, does not go into in good concentration in the liquor. So that is was the aim that we started with the S2SO4. And again, there was another reason was also there, because as per literature, when you are going for solvent extraction, you have to have if you are treated with HCl or HNO3, we have to need some other solvent extraction agent. So solvent extraction, whatever we are having, that is DEPA, and based on that only we started treating this red mud with H2SO4. And literature was also like that only, that if you treat with H2SO4, it will found in that particular deuterion, and then from there we can selectively recover. So we faced a lot of problem during usually leaching efficiency was found to be around 70%, 70% in case of scandium, though other was there, but our objective was to recover scandium only. So we dissolved means leached out around 70% of scandium of 50 milligram per kg. So it was coming to be 35 milligram into the solution. So from 35 to 40 milligram of solution, we when we tried to extract with DEPA, after different number of contacts, the raffinate and etc., and after stripping, and then we cleaned also, because titanium is very much close to the scandium. So titanium also comes, others are also there, but our more focus was scandium. So it came like it's not very good purity, but after recovering around 80 to 85% pure mixed oxide, that again we removed titanium out of that. So titanium was reduced by some, you see H2O2 or a particular concentration of uh, hydrogen peroxide. If you are treating, it will remove titanium. So that part actually we did in our experimentation at JNRDC. But in our joint projects where all four are working, I think we are separating each and every major component first, and then slag is coming. The slag is being treated. Slag is having more concentration, not like 50, it goes to 500 or something like that. So from there extraction is little bit easy, and that is now we are going to tell in the public domain in coming maybe months in July and June. So hopefully India and others will come to know that what are the processes and product and quality are there with the current status of the project success in India. So I will thank again to all audience for their patience hearing, and if there are any question, I hope I can answer to you all. Thank you very much.
Thanks, Dr. Upendra Singh, for excellent presentation. So, Dr. Upendra Singh, you are here, and the session is open for questions and answers. So questions, please go ahead and ask question to Dr. Upendra Singh. Any question? Shankar? Okay. Bharat Vide, please go ahead. Bharat Vide. Or have you given any question? Please go ahead, Bharat. Bharat, please go ahead. Okay. We cannot hear now. My speaker works now. Okay. This is a mess. So I think Bharat, I am not sure where is he. In the meantime, please ask anybody interested. Please ask question to Dr. Upendra Singh. Is there any research is done on Kutch bauxite? There is a question, Dr. Upendra Singh.
Yes, sir. Sir, good evening.
Good evening. Yes. So he's asking, is there any research is done on Kutch bauxite for gallium, vanadium, scandium, and other things?
So, sir, actually, we have not analyzed specifically bauxite, but we have done all the work on red mud, specifically three plants, major plants, particularly critical minerals, and we are more focused on the scandium only, because scandium is now, Niti Aayog actually started working on scandium recovery from fly ash and red mud. So it was a mega project of Niti Aayog only, where we have to see the concentration. If it is if it is around 50 milligram per kg, so we have to think of recovering it from that. So that is what the aim was there. We have not been working or worked on bauxite itself, but at the moment, what other like IBM and GSI has already done, but not specifically bauxite. They have worked on identifying the rare earths in their soil and sediments. But at the moment, what we are doing with IBM, and we have a very good MOU with them, that we have to identify each and every mines of IBM for their dump, tailing, and all, where all the rare earth are there, are all critical minerals are there. So hopefully within 6 months, it will be complete mapping of rare earth and critical minerals from the IBM's, whatever ores or whatever means mines are there from them. So that is what we are doing, but not specifically Kutch or anything.
Dr. Upendra Singh, very good information. Just a small suggestion. There is already a small alumina plant is working in Kutch, as you know, Credo Minerals. If you can get some red mud from Credo Minerals, maybe you can check bauxite and red mud and whether there is a concentration of scandium more than the other red mud. So we should can check a small concentration, if a small alumina refinery there. Anyway, so that's one suggestion. Okay, please go ahead. Some other people, any question? Shankar, any question?
Mr. Maheshwar has raised this.
Not now. Not now. If I think of some questions, I will forward it to you.
Okay. So Chaitali Patakunde, what if proceed for frictional precipitation, that is lime method for gallium recovery? Is that beneficial?
Sir, lime, that is also basically, if you want to remove trace elements from the leaker, lime is one of the treating agent. But if you go with the purity and all, it will not be feasible. It will not be economically viable. So that is what the problem with gallium. Gallium purity is one of the most important part when you are trying to recover extract from bare liquor. But I don't think lime will be the real option for that. There is a very good, information that now Mori is going to set up a plant based on ion exchange, which is more than 99.9%. So I think for gallium, if you want to sell into the market or into the market, you have to have 4N purity. So that is the reason lime and any precipitation methods are not advisable.
Okay. Mr. Maheshwar Vera, is Indian rare earths limited production more than any other industries in India?
No. IRL is the only agency who are dealing with the rare earths. No other industries are there for rare earths, sir. That is true.
Okay. Okay, correct. So please, any other question? Anybody else? Okay. Mr. Bera, please go ahead. Unmute, please. Unmute.
Yeah. So that was my question about Indian rares. But Indian rares produce all rare elements from monazite, mostly from monazite. And but except monazite, other minerals are available in bauxite, as indicated. But does it contain in other minerals like any laterite or any deposit of iron or coal?
Yes, we have been actually identifying the resources, particularly primary, as you know, that monazite is the real source, and this sand is the main source of our rare earth. But as per my knowledge, there is no primary source for particularly scandium and rare earth are there. There are many rare earths which are like heavy rare earths are there. Their minerals are there. But for scandium, we don't find any specific mineral which are having in percentage or something like more than 100 ppm. So that is why we are more dependent on the secondary resources only. And the best resource which we have been seeing or we have been observing that red mud and maybe bauxite is the main source maybe for the recovery of scandium. Even gallium also the same story. Gallium also is having the same thing that main source is bauxite only. So that is why these two are more or less equally important, and main source is bauxite and processed residue.
Okay. Any more?
Okay.
Yes.
Any more questions? Okay, ladies and gentlemen, the presentation will be available on IBAAS website. Thanks to Dr. Upendra Singh. And you can direct questions to IBAAS or Dr. Upendra Singh, and IBAAS office can coordinate and get a reply from Dr. Singh, Dr. Upendra Singh. So thank you very much, everybody, for participating in this interesting topic and interesting presentation of Dr. Upendra Singh. So IBAAS will coordinate any more questions on the subject. Thank you very much. Thanks to everybody. Goodbye.
Thank you, sir. Thank you so much. Thank you all.
Thanks.